Sage.
Okay, let me start by thanking the organizers for the organization of this nice conference. And yeah, it's nice to meet every year, and I hope that this will continue for several years in the future. And thanks also for the invitation to speak, of course. Today I will talk about work that we are doing in collaboration with Anders Corinucci, that is here, with Marco Fazzi and Dave Morison. It's it's almost finished, but we didn't put any number here because we never know. So what is about? This is about, basically it's written in the title. You see in the title, there are two parts. The first part is referring to a subject in F-theory that has been studied a lot. And we understand many things, but there are still open issues. And as we have seen from the previous talk. And the other is matrix factorization. This is a technique that is not new in physics. And in fact, it's a pleasure to speak just after Hans, that was deeply involved in this work. Anyway, the introduction of a matrix factorization in F-theory is quite new, is quite recent. And the reason why it could be a powerful tool in F-theory is that it allows to deal with singular spaces directly without the need of resolution. Now, of course, resolution is a powerful tool, and we all use this tool, and we got a great result with this tool. But I mean, we know that F-theory sometimes requires a singular space. And sometimes we cannot resolve it. The singularity is the resolution is obstructed. For example, in the presence of T-brane or singularities that cannot be resolved. So developing tools that allows to deal directly with the singular spaces is could lead to interesting results. Okay, let me give some details of what I said so far. So, well, this has been explained very well in Miriam's talk, in Watti's talk, and previously. So abelian gauge theories in F-theory are due to the reduction of the C3 form potential along harmonic 2 forms in the compact manifold, along this way. Now, these 2 forms can be described by its Poincare dual cycle, that is a divisor. And okay, so in M-theory, actually, each divisor give a massless U1. In F-theory, the situation is more complicated. And in fact, in an elliptically fibered threefold or Calabi-Yau manifold, one needs to have an extra section in addition to the zero section in order to have a massless U1. Yeah, the technique, as I said, I mean, has been introduced several years ago. And been studied a lot continuously during these years. And in this talk, I want just to show you how, by using matrix factorization, we can actually detect this extra divisor that we need to have massless U1 in F-theory. Okay, so what is the simplest situation in which we have a U1 gauge symmetry in F-theory? This was named as U1 restriction. If you are familiar with the Tate form of the Weierstrass model, you just take the E6 coefficient and you take this to be a squared. This allows you to factorize the Weierstrass equation in this form. Notice that here we have a quadratic term. This is due to the fact that I shifted the x coordinate in the usual Weierstrass form, and I will use this form in all this talk. Anyway, so after this restriction on the complex structure modular space, the manifold factorizes and takes the manifest conifold singularity. Okay, the conifold singularity is when all these 4 factors vanish, that is at x, y, A3 and B4 equal to 0. If one does a resolution, in this case a small resolution, one sees an exceptional P1. This exceptional P1 will be wrapped by an M2 brane. This P1 intersects an extra divisor, this extra divisor that, on which we expand the C3 form at one point. So the M2 brane wrapping this that is charged under C3 gives, in the low energy action, a particle that is charged under the U1 due to this C3. And the charge is given by the intersection between this P1 and this extra divisor. U1 restriction was actually the model in which matrix factorization was introduced in F-theory, and by Raffaele and Andres, that are here, both here in the audience. And okay, this formalism, as I said, allows to deal with singular manifold without resolution, and one can in fact detect with this the extra divisor that one needs for the U1 gauge symmetry directly in the singular space. One can identify massless matter charged under this U1. Okay, I will review this shortly how. Moreover, the matrix factorization, as we have seen this morning, comes naturally with a way to resolve the space by through the mechanism of non-commutative Crepant resolution. And in some cases, it's also easy to associate a quiver, as we have seen this morning, to this manifold. Okay. So what I want to do in this talk is, first of all, review this simple case, and then show you how we can apply this machinery to a more complicated or more generic Calabi-Yau threefold that have one massless U1. Okay, so let's start from this from the conifold, from the U1 restriction. As I said, takes this factorized form. I will simplify this by calling y plus and y minus these two factors, x and w this fourth factor. Now, this singular manifold has non-Cartier divisors. In this case, I show you two, y plus, y minus, or y plus, let's say, one is y plus equal x equals 0, the other could be y minus equal x equals 0. Now you see that immediately that these are what? These are codimension 2 loci in the ambient space that automatically solve this equation, so are codimension 1. These are divisors. And not only that, these are also a section of the elliptic vibration. You see that they touch the fiber at y equal 1 value, x equal to another value. The singularity here is a codimension 2 singularity in the base and support charge states. Okay, so how can we understand now this situation, which we expect to have a massless U1 and charge states? Well, we can apply a Sen limit to this setup. This is very easy. We introduce this extra. So this is the equation of the Calabi-Yau threefold that is double cover of the base. If we are, this is this is in the case of a fourfold. Otherwise, this is just a K3. Anyway, this is the type 2B manifold, and this is the D7 brane locus. You see that the D7 brane locus splits into two loci, two divisors, that are exchanged under the orientifold involution. The orientifold involution will change xi to minus xi. So these are branes in the same homology class in this Calabi-Yau, and then they will support a U1 gauge symmetry. They also intersect away from the orientifold plane when A3 equals B4 equals 0, and here is the charge matter. Okay, so let's see what is matrix factorization, and Anders already introduced this this morning. So we see that this equation admits a pair of matrices, phi and psi, such that their product is equal to the defining equation times the identity. In this case, it is enough to have 2 by 2 matrices. I'm just reviewing what Andres said this morning. Now, once we have these matrices, we can define the associated MCM modules over the coordinate ring R in this way. Okay, so we define, for example, M to be the co-kernel of this map psi between R2 times the 2R2. What is, roughly speaking, this object here? Well, basically, is roughly this space mod by the image of this map. Now, this map here is a matrix, and you see that on top of the conifold, so on top of this manifold, the determinant of this matrix is equal to 0. Okay, sorry, this S should be an X. So this on top of the manifold has determinant equal to 0, so it is rank 1, and so this space we expect to be rank 1, except of course on the singularity where something strange is happening. This matrix is completely, it vanishes completely, and then here we get something of rank 2. Anyway, we see here something of rank 1 almost everywhere in the manifold, so it sounds like a line bundle defined away from the conical singularity. And it's something that we can define already in the singular space. Okay, we don't need to make a resolution of the space. But, I mean, just to get confidence of what we are usually, on what we are used in for the conifold, we can resolve, make a small resolution in this way. We enlarge the ambient space by considering an extra P1, and we substitute our defining equation by these two equations. You apply this matrix here to the coordinates of this P1. Now you see that when this is when some of these elements here is different from 0, this is rank 1, so we fix a point on the P1. On the other hand, at y, when all these 4 are equal to 0, this is automatically satisfied, and so we get the full P1. So this is how the P1 blow up out of the singularity. Now, introducing this P1, we are also introducing a line bundle that is actually the lift to the smooth space of the module that we have seen in the previous slide. Now, to this line bundle, there is an associated divisor. This is the first class. And how this is defined, this is the locus where a generic section vanishes. Now, a generic section of this line bundle is simply given by this, where sigma 1 and sigma 2 are coefficient. These are the coordinates L1 and L2. Now, what does this? So, if we intersect this with this equation, we see that also these equations are satisfied. And this, in fact, define this divisor in the blowdown, once we blow down the exceptional P1. This extra divisor, so this divisor here, is manifestly intersect the P1 at one point. Okay, so we have obtained this divisor, this extra divisor, in the singular space by going to the resolution, then finding this divisor, then blowing down, and we get this. How can we get this expression directly in the singular manifold? Well, just realizing that, in fact, this object here is rank 1, so we also expect that its section will be generated by, the extra divisor that we are looking for is the locus where a generic section vanishes. Now, the section we are looking is a section of this module. This module is isomorphic to the image of the dual matrix. So we can simply write this a generic section of this object, like by this equation, and we see that immediately obtain the same equation that we had in the previous slide. So what we have obtained, and then we obtain this directly in the singular space, we obtain a family of non-Cartier divisor, among which actually there is the extra section, or the non-Cartier divisor that I showed you before. If you put sigma 1 equals 0, sigma 2 equal to 1, you will see that we get the divisor x equals 0, y plus equal 0. Okay, so this was the simple U1 restriction, or the conifold case. What about a generic case in which the elliptic fibration has one U1? So this is the Morison-Park model, okay, that has this form. Again, maybe you don't see it immediately because I shifted again the x coordinate, okay, but this is the Morison-Park Calabi-Yau threefold. What we know about this, we know that it has a rational section that is connected to the fact, so whose extra divisor is then giving a massless U1, and then we have two curves of conifold singularity, not just one. And in fact, we have curves with the support matter with different charges. One has charge 1 and the other has charge 2. Can we understand this at weak coupling? Well, let's apply the same limit to the Morison-Park. This is done by taking this scaling and then sending epsilon equal to 0. The Calabi-Yau, the type 2b Calabi-Yau double cover of the base is given by this expression. Identity involution is chi to minus psi. And then the D7 brane locus splits into these two that once we intersect with psi actually splits into 3. So we have, at weak coupling, 3 branes. 2 are imaged to each other, and 1 is an invariant brane. So in this setup, we actually expect, again, 1 massless U1. So we are happy. We obtain the same that we expected directly from F-theory. What about the matter curse? Well, the matter curse happens in type 2b at the intersection of the branes. So let's take one of these branes intersected with that. Remember, this is the U1 brane. You have a matter localized at the intersection that is charged. So it's a B fundamental, but this supports no U1, so it is charge 1. So this is actually this state that lives at this intersection. On the other hand, we have a charge 2 state that lives at the intersection of a brane and its image. Here, at the intersection, we have a B fundamental of a brane and its image that is basically asymmetric of the U1. Asymmetric U1 has charge 2. Okay, so in type 2b, we see that there's no surprise to have a charge 1 and charge 2 states. Okay, now one could ask, okay, is there a 2x2 matrix now describing this Morison-Park model? Maybe this is a generic feature that massless U1 are connected to 2x2 matrices. And in fact, this is not true. What we instead can have is, and we have for the Morison-Park, is a 4x4 matrix factorization. How can we see what is this matrix? Well, we see this by noticing that one can obtain the Morison-Park threefold just by considering this sixfold that is called the universal flop of length 2 and making these identifications. Okay, so this manifold was proved to have a 4x4 matrix factorization, and this matrix factorization is also valid for Morison-Park. And this is the matrix. Okay, so a matrix factorization means a pair of matrices such that the product is equal to the polynomial times the identity. And the two matrices are this B1, and I don't show the other one because of lack of space, but it can be easily obtained by this expression. Okay, so now we have this 4x4 matrix. It's more complicated than a 2x2, as you could imagine. How can we extract now the massless U1 and the charge matter from this matrix? Now, notice that now this is a 4x4 matrix whose determinant vanishes on the Morison-Park threefold, but it's especially because the determinant of this matrix is the square of the polynomial. So what happens is that when we are on the Morison-Park threefold, this matrix goes from rank 4 to rank 2. So it goes down to rank 2. Now, if psi is a map of rank 2 between the spaces, will be a modulo 2. In the result, this will lift to a vector bundle of rank 2. So how can a vector bundle? Well, immediate is that okay. What is a first chain class of? Well, this is the locus where two sections become parallel. Try to apply this for the rank 1 of the co. So again, we use the between the co-curve, and we so it's a bit more involved. What we get is this divide. This I mean that what I get here is the divisor defined by 3 equations. Each equation is a combination of sigma I defined by these two. But in principle, we find a full family of non-Cartier divisor, as we obtain also for the conic. Why I chose this specific one? Because we can realize that in the patch B different from 0, this is exactly describing the section, the rational section of the elliptic fibration that we are used in Morison Park. Okay, so in fact, this way of detecting the U1, so among this family, there is the divisor that we expect to generate massless U1. Okay, matter. What about the matter? So the matter is at codimension 2, singular loci, and in fact, if one studies this equation and look for singularities, one finds a long ideal that defines these points. But one of the defining equations factorizes in 2, and here is the reason why we have two matter curves. One will be at b equal to 0, and then all the other things, and another will be when this factor is equal to 0. Okay, so let's connect to the matrix. As I said, the Morison Park threefold is the square root of the determinant of this matrix. Okay, so it's basically the Morison Park threefold is a determinantal variety. Where are the singularities of a determinantal variety? Are over loci where the rank goes down. And here there are two loci. One where the rank goes down to 0, from 2 to 0, and this is this locus, and the other where the rank goes just to 1, and we have this one. Now, remembering of the computation we did before in weak coupling, we realized that this must be the locus with charge 2 and this with the charge 1. Alternatively, if you want, we already know that this is the case because we know the resolution of the Morison Park and we can check that this is the case. Okay, but remember, charge 2 is when the rank goes down from 2 to 0. Rank 1, charge 1 when the rank goes down from 2 to 1. Okay, so how can now get an idea of what is the resolved space? The resolved space in this case is done through a Grassmannian blow-up. So basically we take this matrix, we multiply by this Grassmannian. This is the same space that Hans introduced before. Okay, so what is a Grassmannian? As Hans said, is a quadric in P5. The exceptional fiber here is actually given by 3 equations in the Grassmannian that are linear in P5. These 3 equations linear in P5 select a P2, and then this equation into P2 is a P1. Okay, so it's a quadratic equation in P2 is a P1. So this is the exceptional fiber. Okay, now let's try to understand what how we could see directly from the matrix what is charge 1, what is charge 2. Let's consider charge 1. Now, charge 1, for the charge 1, we can stay in a patch in which that is away from the charge 2 states. And that is easy, we can take B different from 0, this patch. Now, in this patch, the matrix factorizes in this form, in the 2 by 2 blocks, of which the first one is trivial, in the sense that it will generate a trivial module. In the resolution, this generates a trivial line bundle. Okay, so this splits into these two. Now we see that here we have a 2 by 2, and this 2 by 2 gives a 2 by 2 matrix factorization of the Morison Park. That is valid only in this patch, so we don't have a global 2 by 2, but here around this singular locus we have this 2 by 2 matrix factorization. Okay, we have a 2 by 2 matrix factorization, we can proceed exactly as in the conifold. Then we can have a small resolution. We know that the first chain class of the line bundle generated by this psi intersect once this. Of course, one would understand what happens to to the P1 of the global resolution. Okay, this is basically a resolution done locally into dispatch. So one needs to consider the Grassmannian blow-up and see how it reduces in this locus and see what is the relation of this P1 with the P1 fiber of the Grassmannian blow-up. Now, if the matrix splits into this form, it's easy to see that the Grassmannian blow-up just boils down to this. So basically, it can be parameterized by a P1. Okay, so and this P1, so the P1 of the Grassmannian blow-up is exactly the P1 of the small resolution given by this matrix. What about the module? Well, if this matrix splits, the modules will split into the direct sum of a trivial module and the module associated with this 2 by 2. Then the first class will be the sum of the two. This is equal to 0, so it's just that. What is the charge? We integrate over the Grassmannian blow-up this guy. Since this is the same as the P1 of the resolution, this is equal to C1 of psi, we know that this, for a small resolution, is 1. So the charge is 1. So we have seen that it's crucial for all of this that we get a trivial block. Around the singularity, the MF splits into two, one trivial and one non-trivial. What happens around the other point? Well, around the other point, actually, the matrix splits into 2 by 2 block, but the blocks are the same. Okay, each block gives a small resolution, and again, so we have an exceptional P1 and we have an associated C1, whose intersection is equal to 1. Now let's see what happens in the Grassmannian blow-up. Now the Grassmannian blow-up now reduces in the resolution, reducing space reduces in this way. So we actually see that we have. So it seems that we have on the exceptional fiber is a P1 cross P1. But remember that there were also some relation that one needs to impose to do this all the thing properly, and this is simply this relation here that is telling us that the Grassmannian blow-up is just a diagonal P1 inside this P1 cross P1. Okay, rank 2 module splits in two copies of the same module, so C1 splits into this form, and then the charge that is again given by this thing is just twice the integral of C1 over the small resolution P1, so we get 2. And it was crucial to get 2 here, that this psi will split into 2 blocks that were equal. Okay, so now we can speculate. This is my last slide before the conclusion. So we can try to extrapolate and say from the studied case. So we studied a manifold, the Morison Park threefold, that was coming from a flop of length 2. And we got, in fact, a 2 by 2 matrix factorization, and we got a charge 1 and 2. Now, we would like to conclude now that if a variety comes from a universal flop of length L, with an MF that is 2L times 2L, when we have all charges up to L. Over these states, the rank will go down from L to L minus 1 until 0. An example, L equals 3, we expect to have this configuration. For a charge 1 state, this splits in 2 by 2 blocks with 2 trivial and 1 non-trivial. With charge 2 is 1 trivial and 2 non-trivial. Charge 3 should be 3 copies of 2 by 2. So if this is the case, now since there is a result that this length cannot be bigger than 6, then we expect an upper bound on the charge. That was the thing that was mentioned before in what is talk. Okay, so let me conclude. We have seen how to apply matrix factorization techniques in manifold with the massless U1 in F-theory. We have seen that this matrix naturally encodes the extra U1 divisors, and it can be defined already in a singular limit. We have a family of representative of this extra divisor. We have seen the charge 1 and charge 2 matter loci. They come from loci where the rank of the matrix goes down from 2 to 1 and to 0. And the charge is given by the intersection of the exceptional P1 with this extra divisor, and is encoding how the matrix splits around the singular locus. And we have some hint that the charge cannot be bigger than 6. Of course, there are several open issues. first of all, study more complicated geometries, including the one with the length bigger than 2. Check that if this we are able to do this for all the length, the flop of length L, then we could ask how the models that are on the market that have charge 1, 2, 3, and 4 until so far, but maybe in the future will arrive the 5 and 6 models, how they can be accommodated into a matrix that should have higher size. So for the length equal to 6, we expect a 12 times 12 matrix. So you can expect how difficult may be to construct this matrix. And also, the last point that I want to cite is how to apply the quiver techniques to the Morison part. We have just preliminary results. It's not as easy as it was for the Laufer that Andres was mentioning this morning. Okay, that's it. Thank you.
Connection between that 6 and the fact that the elliptic curve has at most Z6 symmetry?
Yes. At most?
Z6.
No, Z6. Well, that 6 actually is connected to the fact that this flop of length L comes from deformations of AD singularities. And the length is connected to the dinking label of the node, and the most that you can have in the E8 is L equal.
No, that is related. That E8 is related to Z6.
Okay, so then yes.
That's the reason. Mm-hmm. And do you have something? But you do get other charges like 5.
No, so far we have just analyzed the charge 1 and 2, but.
But you expect to get charge 5?
We expect also charge 5 because
not just 1, 2, 3, 4, and
the length is 1, 2, 3, 4, 5, 6. So we have all.
Okay, thank you.
So the upper bound of 6. That's for Calabi-Yau 3-folds. What about Calabi-Yau 4-folds?
The expectation is that it should work also for 4-fold, but these things have been studied by mathematicians only for 3-fold. So the theorems have been established only for 3-fold. So I cannot say for sure that for 4-fold. I don't know if Andres agrees on this.
Like, why would there be a Dinkin label argument for the 4-fold case?
Yeah, exactly.
I'll just repeat. I mean, usually the 4-folds we look at in F theory are morally families of either K3s or 3-folds, right?
So here we are talking about codimension 2 singularities. And yes, so the idea is that at least for this kind of singularities, you can see the 4-fold as a family of these singularities. And so, but I mean, yeah, this is just intuition. Could be that since there are Yukawa points, that something was wrong.
And you could imagine there's like orbifolds of C3, and then you have to look at the matrix factorizations for that. But I would presume that the length could be quite high for that case. So you're saying I can't do it?
So, sorry, I'll just speak of these techniques.
No, wait. No, take the microphone. Here, I'll give you the mic.
I mean, these techniques, they should be able to work with things where the resolution is at P1, the fiber of the resolution, then some of it might carry over. So orbifolds of C3 there, you might actually have a 4-cycle as an exceptional thing. And then I think then you're in trouble. At least then these NCCR things are not as clear.
Yeah, I actually have two questions. One question would be, do you have a strategy how to engineer like some geometry which has like a model Weyl group of higher rank, like rank 2? And then the second question would be, because, for example, in this nice work of Nikhil, the charge 4 guys were constructed from a representation, or from a rank 2 model Weyl group, where you had some representation which had charge 2, and then they Higgs and got charge 4. Mm-hmm. And so yeah, do you see a strategy there?
I mean, as I said, these should correspond to matrix factorization that are very large. So far we don't have any idea how these look like. Also, the F and G polynomial for those cases are really huge expression. In case of Morison Park, it's quite manageable. So one should understand how to guess. I mean, at least the matrix. Yeah, I have to say that if we had the universal flop of length 3, 4, 5, etc., then we could try to apply the same strategy and to merge this F-theory model into this. But unfortunately, and this is also an indication that probably there is a link, these have not been constructed. So the explicit expression of universal flop of length L are only up to 2, L equals to 2. This is an indication that already at L equals to 3, it becomes very hard to understand what is the expression. And if we think about the F-theory charge 3 models, we see where the problem could be, because they are a mess.
Yeah, thank you.
Thanks, Roberto, for this beautiful talk.